screen. Do you see my slides? Okay.
Yes.
Okay, good.
So good Monday meeting, everybody. And this meeting is becoming more and more attended each week. And after the nice seminar by Greg Berosa last week, now we have also Werner Marzocchi, that is a full professor in University of Naples, and is one of the leading experts in earthquake forecasting and natural hazard forecasting. And it's a pleasure for me to be host today because Werner has been my professor at university, and I was always impressed by his ability to make enthusiastic about his topic and also to pay attention to check the right question on the problem. So in forecasting studies, it's really important to have the good question to solve the problem. So Werner is a really expert, so have a good talk. And I ask to everybody to mute the microphone to avoid the noise. And please interrupt Werner if you have a question, or at the end of the seminar, we can have a list of questions.
Okay, thank you very much. And thank you, Elisa, for your nice words. Okay, before talking about earthquake forecast, I would like to share with you why I became interested in forecast. Actually, I was a master's student and I was talking with a friend of mine. He was a mathematician, and he asked me, what do you want to do in your future? And I said, wow, I would like to become a scientist. And he asked me, oh, well, interesting. What does science mean for you? What does it mean to be a scientist for you? And I have to say that years later, I read exactly my reaction in a few words written by Sir Peter Medawar, that is Nobel Prize in Biology, if I remember well. And this was exactly my reaction. Ask a scientist what he conceived the scientific method to be, and will adopt an expression that is once solemn and shifty-eyed. That's exactly what I had. Actually, I didn't know what does it mean to be a scientist. I couldn't give any satisfactory answer to a friend of mine. This statement has been published in a very interesting, or at least it was very interesting to me, it's very interesting, impacting article in Nature published in 1987. From the title, you can understand what's going on, where science has gone wrong. And actually, I discovered that it was important to know exactly what science means, just to be able to have a solid answer to the critiques that are usually made to scientists. In this paper, there were a lot of very interesting definition of scientists. This guy on the left is Feyerabend, that was very nice and very clever guy. And he loved to provoke. And actually, the statement that he released was clearly provoking. Normal science is a fairy tale. Equal time should be given to astrology, acupuncture, witchcraft. Of course, behind this provoking statement, there was something very solid behind that. Actually, people couldn't give a satisfactory answer what science is. Probably you know better this guy here that is published one of the most diffused book on philosophy of science is The Structure of Scientific Revolution. And for him, the business of science is not about truth or reality. It's about transient vogues. That's a really strong statement. My friend, mathematician, was a Bayesian, and he was, and his view was very similar to what Dennis Lindley had until the end. He just died very recently. For him, science is not different from literature. It's not different from other human enterprises. There is no reality to discover, just the consensus that makes objective science. Different ways to say almost the same thing. Science does not have any specific characteristic with respect to other kind of human enterprises. And again, still today, there is a lot of concern about what science is. This has been taken by a recent paper on Nature. And for the people that know something about the superstring theory, And according to the theoreticians, say, if a theory is sufficiently elegant and explanatory, it need not to be tested experimentally. So there is no need to test it. That's elegant, that's beautiful, this is science. And I can say the same for a painting. I could say the same for a painting. So again, people can be interested or not in this kind of stuff, but for sure, I realize that we have a problem in explaining exactly what makes science different from other human enterprises. And I am very happy to read this report by AAAS that said the growing ability of scientists to make accurate prediction about natural phenomena provides convincing evidence that we're really gaining in our understanding of how the world works. In this report, they made a lot of emphasis to accurate prediction. It means science has a predictive features that other kind of human enterprises do not have. So that's, to me, was a very strong statement that pushed me to think about this, in the sense that, okay, the only way in which we can make a distinction between science and between other kind of human enterprises, again, is the fact that we are able to make accurate predictions. Yeah, with the word predictions, it's clear that we are talking about the forecast, we are talking about saying something about the future. The term accurate is still important as well, in the sense that accurate means that you are able to take a model, take the data, and you are able to say that your forecasts are accurate. Again, this kind of stuff is not easy at all. It's easy in a laboratory experiment when everything is controlled, but in open system like the Earth, things are, again, are much more complicated. For instance, you are used to, probably you hear many times all models are wrong. So if all models are wrong, well, why do I have to test it? I already know the answer. So again, there is still a universe about understanding exactly what accurate means. But I have to say that we have some satisfactory solution to this word. And this is something that I'm not going to talk about. I'm just simply, with these slides, I'm just simply want to give you, I want to share with you why I became interested in this kind of activities. And of course, this is not a novelty, because, for instance, here one of the most impressive scientists that we had in the last century. Science is only useful if it tells you about some experiment that has not been done. It means the forecast is exactly this. It's exactly an experiment that has not yet been done. It is not good if it only tells you about what just went on. This is also a very important statement because highlight one important fact. The important fact is that when we look backward and forward, we see two completely different worlds. We have to be aware of this, because looking backward, we are always exposed to some sort of hindsight bias, that everything is very easy after the fact. It's not so easy to say something before things happen. So at the very end, I was convinced that forecast is not just an exercise for practitioners, but a way in which we can really demonstrate to ourselves in particular that we are really gaining some knowledge about the process. Only if we can say something before things happen. And this is everything related to the importance of the forecasting enterprise, forecasting the future. So I see a noise from, can you hear me? Can you hear my voice?
See, but there is also a noise, I don't know why.
Yeah, me too. Okay, anyway. So, and good. Now, let's start talking about earthquake forecast. Where are we now on earthquake forecast? And let me introduce you, for the people that don't know it, the wonderful word of ETAs. In the sense that ETAs represent what we think we know now about the earthquake forecast. And the first question is, why ETAS? Why ETAS and not other methods? And again, we think that ETAS is the best performing model so far in prospective forecasting experiment. I don't know if you know the CSEP experiment. CSEP is the Collaboratory for the Study of Earthquake Predictability. It's some sort of international network in which we try to establish some sort of prospective forecasting exercise. For instance, the exercise are carried out in California, Italy, and Japan, New Zealand, Western Pacific, and also the globe, the whole globe. There are testing centers. For instance, now the European Testing Center is at Potsdam. There is the testing center at the SCEC, and so on. They are collecting forecasting codes. That forecasting codes run independently from the authors. And then the testing center also collect the data that really, the earthquakes that really happen. And at the end of an experiment, we try to see if the forecast makes sense with the observations that we have made. This is a purely prospective experiment. And here, for instance, in the SRL special volume 2018, we have collected some of the first round of experiment, what we think we have learned. And so far, again, the epidemic type aftershock sequence is the best performing model. This is just an example about how the information gain that you have from these models with respect to some sort of stationary seismicity, for instance, the seismic as a model over Italy. Of course, every time that you have a swarm, if you have a sequence, you have a lot of gain with respect to a stationary model, but it is interesting to see that also when there is a small seismic sequence, the models tend to overperform with respect to a classical stationary model. So in a few words, it seems that the ETAS is able to capture the time evolution of the seismicity and allows us to make reliable forecasts. Again, I try to be very clear. I'm not saying that we live in a true ETAS world. For now, I'm just simply claiming that ETAS is the best performing. It's some sort of a reference model from which we have to compete. For instance, there are some interesting first attempts to make more physics-based model. The results have been published in the same special volume in Seismological Research Letter. Here, there is some sort of attempt to compare the ETAS model, different flavors of ETAS model, step models that are almost the same, are always based on the clustering of the earthquake, with respect to some Coulomb rate state model based on the including uncertainty or other kind of assumption. And as you can see, this is a pseudo-prospective test because it has been made for earthquakes that already occurred during the Canterbury sequence, but it was made in a prospective way. Again, this is not the golden standard, but it already gives you some information. The basic point here is that so far, this kind of model seems to be reliable in the sense that provide accurate forecasts, but on the other hand, we do not have any model that outperform them. We have also tested the model still in a prospective way during real sequences. This is, for instance, what we have done in 2017 during the Central Italy sequence that I call it a Matrice-Norcia sequence. The Matrice-Norcia sequence occurred in the central part of Italy. This is the time evolution. We identify with different colors, different phases of the sequence. The first shock is the Amatrice sequence, is the Matrice earthquake. Then, a few months later, there was a Visso earthquake. And then, a few days later, the Norcia earthquake. That is the blue one. And then, very close to the end, we got a new sequence in the south part of the region in Campo Tosto, close to a very important dam. Here on the lower left, you see the time evolution, the spatial time evolution. For instance, if you project all the earthquake along this line and you just simply see how they evolve with time, you see that we have an Amatrice earthquake. Then the most productive part was on the north side, where the Visso earthquake occurred, also the Norcia earthquake, and again, still active the north section of the sequence. Then at a certain point here, do you see my cursor? Elisa, vedete il mio...
Yes, yes, yes.
Okay.
Yes, we see it.
Okay, good. You have an increased seismic activity in one specific region, and then they produce the Campo Tosto sequence again and again and again. So again, we released forecast every day, and then at the end we collected the data that really occurred. And what we got is that, just to make a very long story short, the model seems to describe well the number of magnitude 4 that occurred during the sequences. That is this one. The spatial location, if the dots are in the upper part of the plot, means that we forecast very well the spatial distribution of the biggest of the magnitude 4 earthquake. If it is below this red line, it means that the model is wrong. But actually, in this case, we were particularly lucky. And also, the magnitude frequency distribution, the red one is the forecast that we did, and the blue one is the empirical distribution of the magnitude that we have observed. So at the very end, again, the operational earthquake forecast is mostly rooted on the ETAS philosophy, and again, we provide forecast every day in the morning, and we collect the data, and at the end, we compare them in a CSEP style kind of experiment. And again, at the end, we see that something went well. Here, just an example about the forecast that we did, just for specific moment. This is the forecast that we did immediately after the Amatrice earthquake. And the blue ones are the earthquakes that occurred during the time windows. You can see here on the lower right of the plot, the probability for that week to have a magnitude 5 or larger, or 6 or larger during the week. The other three plots are the forecast that we did before the 3 largest events of the sequence. For instance, this one was before the Visso earthquake, magnitude 5.9. The blue one, the map was the forecast, and the blue one is where the magnitude 5.9 occurred. And this was the 6.5 in Norcia, and the forecast that we did it before. And this is the 5.5 in Amatrice. One interesting aspect that I'm going to talk a lot in the next slides is about the weekly probability to have large earthquake. As you can see, we reach at least few percent, not much more than that. And there is some sort of reason for having this kind of upper limit. But again, it's very important that a small probability does not mean that we have a lot of uncertainty. With the test that we have done, it seems that these numbers make sense. What I'm saying is that if we say 2%, it means that is on average the frequency of the expected earthquake occurred 2% of the times. So it is something that has been tested, and so it's not just a number that comes out from the blue or from nothing. Well, okay, this is just to tell you why we think that the ETAS is the best performing model so far. And before going further, before discussing what has been done to go further, just let me introduce you very briefly what an epidemic type aftershock sequence is. It's very nice that people use aftershocks, that Ogata defined this model, epidemic type aftershock sequence, even though we will see this model say that there is no difference between main shock, aftershock, foreshocks. Any earthquake is an earthquake. A much better name would have been epidemic type earthquake sequence, like my Rodolfo Console, a colleague of mine from INGV, was used to say. It would have made much more sense to use earthquake instead of aftershock. Anyway, this is it. This is the equation. We have a background that is some sort of Poisson occurrence of random earthquake, and every earthquake increase the probability to have other earthquake. And this kind of probability decay with time through a power law, that is the Omori law, decay with the seismic moment of the earthquake, again, through a power law, that is the productivity law, and it decay with space with another power law, that is some sort of power law distribution for the spatial distribution of the earthquake. Again, it means that every earthquake can trigger other earthquake. And this way of triggering has been described by these three simple power law distribution. But the most important aspect is the last one, that is outside the square bracket. That is the Gutenberg-Richter. It is very important that this kind of Gutenberg-Richter is outside the square bracket. Why? Because one of the biggest consequences of this is that we can forecast the number of earthquakes, but what can we say about the magnitude of the earthquake? Well, we can only say that they belong to an exponential distribution. It's like to say, okay, I expect 10 earthquakes on average, and the magnitude of 10 earthquakes is, I simply draw samples from a Gutenberg-Richter 10 times, and I see what is the magnitude that comes out from that. And now you understand why we have always a small probability for large earthquake, because it is linked to the probability to sample the right tail of an exponential distribution, that is the Gutenberg-Richter. Again, it doesn't matter the time, it matters the size. It means that before a magnitude 8 or 2 for ITAS model is the same, the magnitude is unpredictable. One instant before the nucleation, we can't say anything about the magnitude of this. I know that there are very interesting works about T0 plus, about what happened just immediately after the nucleation. Here, I'm talking about before the nucleation. And again, for ITAS, and this is the biggest obstacle to get high probability, is that, well, we don't have we don't see any difference between that. This is what we call magnitude independence assumption. There is a lot of interesting work to be done here. I reported some that I recently made with one of my PhD students. We have ITAS model. This is from a very small area in Italy with a very high quality catalog, and here in the Southern California, JMA. And this is the magnitude of the triggered earthquake and the relation with the magnitude of the K nearest neighbor. It means with the earthquake that very likely triggered this one. And again, as you can see in ITAS, there is absolutely no relation. It means that the magnitude of the triggered earthquake is completely independent from the past. Here, we see some sort of small trend, but this small trend is completely removed once we take properly into account the incompleteness of the catalog. What I'm saying is that, in essence, looking at the Southern California JMA, the Italian catalog, once you properly take into account the incompleteness of the catalog, you don't see that the magnitude of an earthquake depends on the magnitude of the other earthquake that triggered it. And this is what we call magnitude independence assumption. And this is, again, this is probably the biggest obstacle that we have in forecasting large earthquake. Okay, so let me summarize some remarks on the physics behind classical ITAS. Again, I'm talking about physics because physics is not only continuum mechanics. There is a lot of people working in physics of complex systems or statistical physics that they love power law distribution. And again, we will see this later, but yeah, for them, the ITAS model makes perfectly sense from a physical point of view. Probably I will show you something in the next slide. But at the beginning, just to tell you, just to put the ITAS model into a framework that is much more familiar with you, ITAS model is compatible with the cascade model defined by Greg and Bill. Yes, a couple of decades ago, in which earthquake triggered other earthquake with unknown magnitude, in which you can't predict the magnitude. So, and again, the magnitude of an earthquake, here I repeat myself, because this is very important to know, is not matter of predicting an earthquake. For instance, one day after Amatrice, I could make a perfect prediction. Tomorrow, I will see at least one earthquake. There is no doubt about that. The problem was about the magnitude. And again, so the biggest limitation in getting high probability of large earthquake is to understand exactly what happens before large earthquake with respect to small earthquake. If the ETAS world is the real world, it means that we can't see any precursor. We can't see any precursor in the pure ETAS world. And again, I repeat, this is the best performing model, but I think that nobody strongly believes that ETAS is the real, is the true word. But again, we have to be honest and say, okay, this is a reasonably good starting model. We have to beat it. And again, talking about a little bit more about the physics, I had the opportunity to work a very good physicist in Israel that is one of the father of the complex system, the physics of the complex system. He told me, wow, yeah, I understand that it is born as a stochastic model, like some sort of Oakes process. It's purely based on empirical observation, but the structure is very common to what we see in complex system. There are many power laws. There is also self-similarity that are ubiquitous. For instance, the Gutenberg-Richter and Mori laws have been found also as an asymptotic behavior when you increase the complexity of a numerical model. Again, just to make a long story short, in complex system, what really makes the difference is not the physics of the individuals. It's much more important how the individuals interact one against each other. So what you see in the physics of complex system, you see that there is some emerging phenomena that looks like very similar, even if the entity that interact one against each other could be some neurons in the brain, could be humans, can be social media, whatever you want. Again, but the way, if there is some similarity in the way in which this entity interact one against each other, you can see some sort of emerging phenomena. And again, the ETAS is much more embedded in this kind of physics rather than in the classical continuum mechanics. And of course, we are going ahead. I'm not going to spend too much time about this, but there are ongoing efforts to make ETAS model a little bit more evolved. For instance, here I just reported the work made with people in Israel, in which we see that some power law seems to have a break in scale, in time, and in space. It means that the exponential of the power law seems to have a breaking slope, a sudden change at a certain point for specific critical point. If we are able to introduce this also into an ETAS model, maybe we can still improve our forecasting capability. I know that Petrillo and Lipiello are doing something, including some sort of the foreshock activity, and Nandan, Shyam Nandan from ETH is doing this kind of model in which the parameter can vary in space and time. So again, there is a lot of things that are going on here. But for the second part of my talk, I want to talk a little bit more about the world beyond the ETAS, because again, there are still some empirical evidence that push us to think about how we can improve this kind of models. And again, I'm not pretending to be exhaustive here. I'm just talking about two points. I just mentioned the pre-sleep stuff that has been already very well described by Bill Ellsworth in the previous talk. But here I'm talking a little bit more about the foreshock. I'm talking a little bit more about the B-value variations before large earthquakes. So again, this is a slide that has been taken by the work by Bill Ellsworth. And I see, for instance, that for Izmit earthquake, this kind of discussion is still ongoing, and probably we have to wait a little bit more to understand exactly what's going on. For instance, for Izmit, you have some paper that say there was pre-sleep activity before that, for the same earthquake, using different set of stations, seismic station. You see a completely different scenario in which the earthquake occurred like a cascade of events. But again, this is something that Bill has already mentioned before. There is not only one thing that I would like to tell you is something about L'Aquila. There was some colleague of mine that has very sophisticated instrument for deformation, not very far from the hypocenter of the L'Aquila earthquake. And they just create some sort of upper limit of pre-sleep that you couldn't see with this instrument at that distance before the 6.3 earthquake. But again, even more important, a few years before, they published a paper on Science in which they show that they have a lot of slow sleep events that are much stronger than the ones that you could have had before the 6.3. So again, it's not a matter of looking at pre-sleep activity before a main shock. It's also very important to see if there is some scaling with the magnitudes of the event, or if there is also some, how can I say, how many times this kind of pre-sleep occur without any earthquake. And this is actually my final remarks. Again, from an outsider, because again, I don't spend too much time about this. I'm working more on different things. But again, looking at the literature carefully, I hope, it seems to me that the pre-sleep stuff is still very anecdotal, in the sense that you publish something, very strong evidence, and some other people publish a completely different evidence with respect to other earthquakes. And to me, one important aspect, and I know that there is some people at La Sapienza in Roma that seems interested in this, is to see if laboratory experiment can show us some sort of different pre-sleep activity before small and large earthquake, or small and large fracture. Because to me, this is even more important. Predicting the size probably is even more important than predicting the time. Again, this is just my personal view, but based on what we think we know now, in which the magnitude of the earthquake are completely independent from what you see, from what you can say before. Anomalous foreshock. Before talking about foreshock, you have to define what a foreshock is. Again, this is a very long story. In the ITAS model, there is no distinction between foreshock, aftershock, and main shock. There is a very interesting technique that Ilya Zaliapin was one of the promoters, in which if you plot the earthquake in scale time and scale distance, you can see that the earthquake tend to cluster into separate distribution. One is the Poisson, this one, this is the triggered part. And again, just to make a very long story short, you can define, for instance, using some sort of straight line, you can define what is the background and what is being triggered. So, and again, once you have a triggered sequence, you have a sequence of triggered earthquake, you can take the largest one and you can call it main shock. And this way you can make a distinction between that. Again, anomalous foreshock. For instance, there are some papers that say there is an abundance of foreshock with respect to ITAS. Here, I just reported a couple of papers. This is has been published a few years ago by Stephanie Seif et al. Here, this is just came out from Petrillo Lipiello, and I see that a very recent paper, but you have seen the presentation by David Marsan, show that there is some cases in which you have some foreshock activity that cannot be explained by ITAS. And again, I'm not going to explain the detail, but the point from this plot is that what we see in reality is that the number of foreshocks tend to be higher from what you expect from an ITAS model. And this is an anomaly that we are looking for to make a step forward with respect to ITAS. Here, this is the work that is still ongoing, made by Esther Manganiello, that is PhD, working with Marcus Herman and me, in which we have analyzed for main shock from 4 to 5, 5 to 6, 6 to 7, and above 7 in Southern California. And we produce synthetic catalogs from ETAs that has been set for Southern California. And the blue curve is what you get from synthetic catalogs from ETAs. And the red curve is some sort of, let me see. And the red line represents the 99 percentile. It means that if you are above it, it means that what you see in the real catalog is something that you can't explain with a synthetic catalog. And again, here the column is the forest shock are between 2.5 and 3, from 3 to 3.5, and so on. Different class of forest shock. And for now, just remain focused on the real catalog, that is the dashed dotted line here. From all this plot, you can see that the biggest difference with respect to ETAs are for small main shock. For small main shock, you have a much larger number of forest shock with respect to what you expect by ETAs. It's not for old main shock, but mostly for small main shock. Again, this pushed us to think about, oh, wow, but maybe there is some sort of interaction with the swarm activity that we know exists in Southern California. And what we have done is to use still the Zaliapin procedure to make a distinction between sequence and sequence, in the sense that, for instance, you can calculate the average leaf depth, that is this D value. When it is large, it means that you have some sort of sequential of triggered earthquake. When you have a small d, it means that you have a tree, that every earthquake can produce a lot of triggered events. Here you have much more linear sequence. And when we calculate this parameter for the synthetic catalog from ETAs, you see that it's very unusual to have a d larger than 5. But in the real catalog in Southern California, we see that some sequences have a d larger than 5. So we decided simply to remove them because they are anomalous with respect to ETAs. If we remove them, what you get is that the new catalog is pretty well described by the seismic sequence, by the ETAs model. But what can we say more about the sequences with the high leaf depth that we have removed? Here, the sequence that we have removed are the red dots that you can see here, and we have made it in a correlation with the heat flux map that Zaliapin Benzion published a few years later. What I'm saying is that most of the sequences with small magnitude main shock and high average leaf depth that we have removed are mostly in area with a very high heat flux. Zaliapin Benzion suggested that this kind of parameter could be used to make a distinction between swarms and not. Here we are just focusing on the forest shock activity. They were focusing on the old sequences. But for now, again, it seems that most of the anomalous forest shock activity in Southern California are simply due to swarms, not to forest shock sequence that occurred before significant earthquakes. Then, another different aspect of anomalous forest shocks is the spatial distribution. The spatial distribution is described by this plot in which the empty diamond are the forest shock. This is the distance from the main shock. This is some sort of distribution of that. And the empty diamonds are the aftershock. And of course, as you can see, this is for the largest main shock in which they reach a longer distance, of course, because the magnitude of the main shock is larger than the magnitude of this one and of this one. But what surprised us is that also the forest shock seems to rescale with the magnitude of the main shock. This is completely unexpected by ETAs. In a very recent paper, again, that I mentioned before, we found some similar stuff. Again, looking at the Southern California and the Japanese catalog, we see that the magnitude of the triggered event, here, let me take the cursor here, the magnitude of the triggered event are related to a longer distance with respect to the barycenter of the sequence. And this is compatible to what we have said before. And this can simply say that the largest aftershock tend to occur on the edge of the sequence. Never, almost never. Some people say never in the middle of the sequence. In particular, when the sequence is very productive. So, and again, this kind of stuff cannot be explained simply by an ITAS model. But again, this is probably the most robust difference that we can see, is that, well, for an ITAS model, the most likely point where you have a large earthquake is just in the middle of the sequence. What we see is that tendentially small magnitudes do occur everywhere, but the largest aftershock tend to occur on the edge of the seismic sequence. Again, here I repeat myself, anomalous foreshock sequence seems to be related to swarm activity. So it is true that some sequence cannot be described by ITAS, and most of these sequences seems to be related to a swarm activity that occurred, for instance, in Southern California in high heat flux zone. This is something that the work that we have been doing is still ongoing, and we are trying to make, we have to find also some other kind of relationship. The spatial distribution is different from what expected by ITAS. Again, probably what we have seen is that the largest aftershocks, the largest triggered events occurred not in the middle, in the most active part of the sequence, but mostly on the edge. And this is something that ITAS model can't tell you. Variations of the b-value. This is the last part of my talk, is about the variation of the b-value. I have to say that it's frustrating to me, because the b-value is probably the easiest thing to calculate from a statistical point of view. You have distribution, exponential distribution. You have just one parameter of this distribution is the b-value. But it is so complicated in reality. So we can be fooled very often if you don't care too much about the quality of the data that you have been using. Again, this is just a few of examples. For instance, the low b-value before strong event. If you calculate, for instance, the b-value, you generate seismic sequence, you generate earthquake catalog, in which the b-value is equal to 1, and you see, and you calculate the b-value again from this synthetic catalog, you see that there is a strong correlation between the b-value and the maximum magnitude that you have in your data set. So it means that if by chance I have a strong foreshock, I must expect that the b-value has to be lower than 1. Even if there is no physical reason, it's just a mathematical motivation. And then if you stack all the sequences in which you have strong foreshocks, you always have a significantly different b-value, low b-value. For instance, here, again, we have generated synthetic catalog with b equal to 1. And then when we stack the foreshock sequences, this is the b-value that we calculate. The b-value is the yellow line, and you see that most of the simulation has a smaller b-value. And you can easily check if you stack, you can get a significant low b-value, even though it is not significantly smaller. It's just a mathematical artifact. This is for the low b-value before strong event. But with Marcus, a recent work that we have made with Marcus Herman, we have seen that when we try to calculate the b-value for high quality catalog, the situation becomes even more complicated. Here, for instance, is just an example. I try to get the main point here because we have made a lot of things using the Southern California high quality catalog. And then the first thing that you want to do is just to calculate the completeness. If you use the classical procedure, you see here in the yellow one, you see the circle and the square. And you have a b-value that was about 0.7, 0.8. But if you decided to choose as a completeness magnitude, the magnitude above which the magnitudes are really exponential, because again, you can calculate the b-value if the distribution is exponential, because if it is not exponential, the b-value does not have any meaning. Then you see that the completeness magnitude is much, much higher. And here, it is here when the b-value is around 1. So again, here just to tell you the difficulty to find the completeness. And again, please check always, every time that you calculate the b-value, check if the data that you are using are exponentially distributed. This is a minimum requirement. Then we see also that part of this curvature is not only due to incompleteness, but due to the fact that most of the time the catalogs are emerging of different magnitudes, and this can create a problem. Again, frustrating, but you have to know that if you want to give some sort of meaning to the b-value, you have to be aware that the situation is probably more complicated than just simply crashing the data with the code and getting results. It's probably a little bit more complicated. The last point is variations of the b-value. B-value of what? In the sense that, for instance, sometimes we take a region, we calculate the b-value, and so on, so on, so on. Again, here is a recent paper that we published on BSSA. We just simply select an area around the lander's fault that has been triggered, that has been involved in 7.2 earthquake, and then we see what is the frequency magnitude distribution of the earthquake inside the red zone and outside, and you see that the distribution is completely different. It's completely different. So again, when calculating the b-value, you have to be aware where you are, because if you are just calculating the b-value inside the fault that are just slipped, you have to expect that probably the magnitude frequency distribution will be smaller, will be different from the earthquake that just occurred outside. Of course, this kind of difference can be modeled with the difference b-value, or we propose something different. We propose that the corner magnitude depends on the elastic energy available to create an earthquake. So if I have a zone that had just had a major slip, probably in that part, the nucleation of an earthquake cannot be too large. And this is what we call a corner magnitude that depends on the energy. Again, I'm not going too much into the detail, but the idea here is that when you calculate the b-value, if you calculate the b-value for the whole area, you are putting together two completely different things. This situation is even clearer for another paper that we have that is still in preparation, that we made with Marcus Herman and Esther Piegari. For the central part of Italy, we strongly benefit by a very nice project funded by NERC and National Science Foundation, and that is focused on the central part of Italy. Part of this project was to prepare very high quality seismic earthquake catalog there, and we use one of them that has been just now submitted to seismic record by Tan et al. It contains almost 100,000 events of magnitude MW 1.5. They made a lot of effort trying to make homogeneous the magnitude, and this is still this is a good point. Anyway, here we just map this catalog, and we identify 1, 2, 3, 4 main cluster, main structures. Amatrice seems to be a world apart, in which there is no earthquake close to the main shock. But here we identify here some sort of clustering. This is what we call piattone, because it seems a very flat layer. And this is the part of the that has been triggered by the magnitude 6.5 in Orcia. This is the 5.9 in Visso, and this was the magnitude 5.5 in the south part of the sequence. If you look at the magnitude frequency distribution, how it evolves in space across these clusters and in time, you see some sort of things that is really surprising. For instance, again, this is some sort of timeline. Again, Amatrice, there was a lot of red point. It means that the red cluster has been activated after Amatrice. Here there is Visso, that was mostly the red cluster. Then again, Norcia earthquake, there is still a red and green. And the last one, Campotosto, that was the pink and the blue. So again, you see that the clusters are very, very close one to each other. But again, if you look at the magnitude frequency distribution, they behave completely different one from each other. For instance, let me focus on what happened in the red cluster, where the Norcia earthquake triggered. Amatrice, Visso, all the other big earthquakes are outside. This was the section in which the Norcia earthquake nucleated. This is the magnitude frequency distribution before Amatrice. This is the magnitude frequency distribution just immediately after Amatrice and before Visso earthquake. Then we had Visso earthquake that was in the green cluster, but what happened into the red cluster is that we got a very completely different magnitude frequency distribution. And again, notice the B value increased a lot with respect to before, in the place where the Norcia earthquake will be triggered 1 day, 2 days later. So again, before Norcia, we see an increase into the B value in that specific portion where the earthquake nucleated. And again, the last one is this one, is what happened in the magnitude frequency distribution after the Norcia earthquake. And again, we still have an increase into the B value. Again, for this specific cluster, the time evolution of the sequence changed completely the magnitude frequency distribution of the earthquake occurring in that specific cluster. For the blue one, nothing changed. This is the distribution before Amatrice, this is after Amatrice and before Visso, and this one was after Norcia. Nothing changed. The blue one, again, I will show you again, the blue one here, the magnitude frequency distribution was unaffected by the sequence. Here, the red one has been subjected to many important, significant variations into the magnitude frequency distribution. So, few final remarks about the variation of the B value. An unbiased estimation of the B value requires that you check the exponential distribution. Again, the B value makes sense only if you assume that your data, your magnitude, has an exponential distribution. If the data do not follow an exponential distribution, the B value could be completely misleading. So please just check it every time that you do this calculation, because often an anomalous B value may derive simply because the data are not exponential. The second one is the magnitude frequency distribution varies in space and time in contiguous tectonic structure. We have shown what happened, for instance, during the central part of Italy. We are not able to understand exactly why, but there is a very clear evidence that the magnitude frequency distribution cannot be considered like in ITAS, some sort of stationary model in which you have exponential, you have some sort of magnitude frequency distribution that remain constant through time. It seems that there is important variations on that. And once we will be able to include it into an earthquake forecasting model, probably we can get some good improvement in the forecast. So again, the last slide, earthquake forecasting Quo Vadis. So let me tell you, I thought a lot about these slides. I have to say that predicting the evolution of science to me is maybe more difficult than predicting earthquakes. So I don't want to define any clear path for the future. So what I reported here is just based on the experience that I got so far. Forecasting the size maybe is more important than the time. So it would be very interesting to see scaling law for precursor depending on the size of the earthquake. I think that this is really important to see, because this can break the magnitude independence assumption that is, again, the biggest obstacle that we have. The second point is that I added the second point because I fall in love for this paper, The Quiet Revolution in Weather Forecasting, that have been published by Bauer et al. In Nature. And they show that in 30 years, they didn't do any breakthrough discovery, but they simply add, step by step, they make their model much more solid from a physical point of view, adding more information. So step by step, at the end, after 30 years, they got models that are much more reliable than 30 years before. This is what we call brick-by-brick approach. And again, now our limit is few percent per week. Once we got 20% per week, again, believe me, this would be a revolution. Even if we are not able to predict exactly, but just getting 20% or 25%, it would be a huge step ahead with respect to what we know now. And the last point is something that I always love. Dave Jackson told me many times, and I think that is very important for any young researcher. Independently from the idea that you have in mind, please think about how my model can be tested, how my model can be tested with independent data. This is, again, really important, really, really important to demonstrate that you are getting more knowledge about what we know now. And that's it. Thank you very much for your attention.
Grazie, Warner. Thanks. Please unmute and clap everyone together.
Nice one.
So for the question, if there are younger researchers, it's better. Otherwise, anyone is welcome. Raise your hand and this is the first. Catherine, okay, go ahead.
Let me see if I can you hear me?
Yes.
Okay. So there's not usually much, correct me if I'm wrong, but there's not usually much comment on the spatial predictability of these models, right?
Well, yes and no, in the sense that even if the ETS model are isotropic, but for instance, can I show you again one slide that I showed you before? For us, for instance, when we apply this kind of stuff to the Amatrician-Notch sequence, here you see that we have some sort of spatial skill. I strongly believe that this is not the best that we can do, absolutely. But again, there is some sort of spatial skill, or at least we are testing this in, we are testing this in with statistical tests, and then we say, okay, we have some skill. But again, I strongly believe that we can do much better, but we don't know exactly how, for now, at least.
Yeah, so then I